Our last speaker before the discussion and the break is Nathaniel Martinez, who will be presenting classifying scanning precipitation radar images using autoencoders. Nathaniel, are you there?
Let me just share my screen. Can everyone see my screen?
Yeah, looks good.
Yep.
Can you put it in presenter mode? There we go.
Great. So, hello everyone. I'm just gonna present the results of the research that I did over this past summer with the help of Ben Blasik and Bobby Jackson, harnessing machine learning to cluster radar images. And so first off, a little bit about me. My name's Nathaniel Martinez, and I'm a second year at the University of Chicago. I'm double majoring in computer science and environmental science. And everything you see here stems from an internship I completed at Argonne this past summer. And so today I'm going to go over the process of creating the convolutional autoencoder I used, the clustering algorithm, the results, and then where this research can go from here. And so the focus of our research this past summer was to understand how and why a clustering algorithm might choose to group certain radar images together and how that might align with our predictions. We did this out of curiosity, just looking at the potential applications of machine learning with radar imaging. And so the autoencoder's main purpose is dimensionality reduction and learning how to recreate the images we input into the autoencoder. And for our data set, we wanted to see how the radar images are clustered. And so for that reason, we made the autoencoder learn unsupervised, which is where the autoencoder simply takes in the radar images without any labels or classifications. And these images then go through layers of compression, ending up in the latent space where the features are extracted. And then once compressed, it's the autoencoder's job to recreate the original image using the data it learned from the prior images. And when working correctly, autoencoders are essential in cluster analysis. And in order for this to happen, it requires around 100 run-throughs of the data called epochs to learn how to recreate the image. As for the structure of the autoencoder itself, the various layers that make up the autoencoder are at the right side of the screen. They take in the original 256 by 256 by 3 color image, and then it compresses it into the autoencoder. It arrives at the latent space with dimensions 32 by 32 by 16, and then it's decoded back to the original 256 by 256 dimensions, hopefully containing a similar image to that of the original. But what exactly were we putting into the autoencoder? We used NextRad AWS to pull right around a year's worth of data from the Chicago radar. And after downloading that data, we generated 900 by 900 color images, which is at the top right. And these images were clearer than the ones we ended up using for the autoencoder and the clustering algorithm. But we decided to reshape the images down to 256 by 256. We did this not only to increase the speed at which we were able to generate the radar images, but it also decreased the time spent encoding the images since it was a lot less computationally intensive. More importantly, however, it was able to still preserve a lot of the original features that were present in the 900 by 900. It was just in a lot less data. Originally, we trained the convolutional autoencoder to train for around 100 epochs. And amazingly, only within a couple of epochs or so, it was able to have an error rate well below 1%. And considering it was analyzing 20,000 images, it was really impressive and a bit suspicious. And so we looked at the results, and the autoencoder was actually outputting, a blank image, absolutely nothing. And as it turns out, it doesn't rain every day. And so a lot of the images we were inputting were just blank radar images. And so we had to, and so there was that oversaturation, and we had to remove a lot of those images. We went back to the radar images, and we calculated the average amount of reflectivity and removed a lot of the images that had no reflectivity present. And that reduced our data set significantly from around 20,000 images down to around 2,000 images. But these images were actually meaningful. They had radar images on them. And so we used an autoencoder to vectorize the images. And so vectorizing is essentially just turning the images into a vector, since you can't quantify an image by how it looks like, since obviously a computer can't do that. And so to calculate the number of ideal clusters, we used the elbow method. And it turns out 4 clusters or 4 groups of images is optimal. And so in order to actually group the images, we used k-means clustering. The clustering algorithm first assigns a mean within the data, which is at the bottom left, and then each vectorized image is grouped into a cluster depending on which mean it's closest to. And this is recalculated, the groups are made again, and you keep doing this until they start to converge. And once they converge, you have the distinct radar clusters. And so how do they end up being clustered? Well, broadly speaking, they were categorized into one of 4 groups: clear air, isolated rain, widespread rainfall, and then severe convection. As I said earlier, we had problems including too many clear air images in the data set, since it made up a majority of the data set, but we didn't want to completely exclude it. We just wanted to make it unfavorable for the clear air images to be selected into the data set. The isolated rain cluster was also expected, since there was enough reflectivity for the radar image to be included in the data set, but not enough for it to be considered widespread or severe convection. And then the 2 other clusters, widespread rainfall and severe convection, are on the right. These classifications, we came to these conclusions largely just by looking at the pictures, but we really wanted a more quantitative approach to these clusters. We just didn't want to say it looked like widespread rainfall. And so in order to reach a more quantitative conclusion, we turned to heat maps. Heat maps plot the average reflectivity over the area the radar scans. And so it gives us a better picture of how often and how severe the convection may be. And so we pulled the raw reflectivity data from the original files, which were in polar coordinates, but we found it easier to create heat maps with Cartesian coordinates. And so we converted that over to Cartesian and then generated the heat maps. And they did prove to support our original conclusions. The image on the left is the clear air cluster. It's fairly empty, barring the ground clutter that's present. And obviously with no reflectivity present, you would expect little on the heat map either. And on the right is the isolated rain cluster. And the results are also to be expected. Although it doesn't seem that much difference between the clear air cluster and the isolated rain cluster, there are areas in the heat map that are more filled in, notably towards the top of the image. And finally, widespread rainfall is on the left side, and then severe convection is on the right side. At first glance, my intuition told me that the results should be reversed, but these results do end up making sense. The widespread rainfall cluster has more consistent, albeit lower convection than the severe convection cluster. And as a result, when it's taken as an average, the reflectivity for the widespread rainfall should be higher than the severe convection, which only sparsely has high levels of reflectivity. And so these results did end up aligning with our predictions. This is not to say that the results were perfect. However, there were some instances where isolated rain images were grouped with clear air. And so we could continue to refine the accuracy of the clusters. And we would also want to reproduce the results with a different year's worth of data to see if similar conclusions are reached. Overall, though, it does provide a strong foundation for machine learning as a tool to classify meteorological data. And so I just like to thank again Bobby Jackson and Ben Blasek for their encouragement and their experience throughout the summer. I'd never done machine learning before this project, so learning to use all the tools like Keras, TensorFlow, Bebop, it was really interesting for me and a lot easier with their help. And as a result, I definitely see myself interested in continuing this in the future. And I'd also like to thank the Career Advancement Office at the University of Chicago and Argonne for the funding I received. This wouldn't have been possible without their support. I also gained a lot of meteorological knowledge as well. I've been interested in this field for a long time, and this was the first time I was able to really go into depth when I got to Argonne, and I'm so grateful for that. And with that, I'll just open up to any questions or comments.